Hi, everyone. It's great to see you all here. Welcome to my thesis defense titled Wearable Data Synthesis for Portable Biomechanics. If I haven't met you before, my name's Owen. It's great to meet you. Yeah, before we jump into the research presentation, I just want to say, yeah, so the question and answer portion is at the end. So as we go along, if you have a question pop up, feel free to maybe write down the slide number so we can refer back to the appropriate place. Also, before I jump into the presentation, I'd like to just start by humbly thanking and acknowledging everyone who made this work possible that you're about to see. So first, of course, thank you to Annie and Sarah, who are my advisors throughout this time at CMU, who have been wonderful mentors and supporters throughout the year. It would not be possible for me to be at this place if it were not for them. So thank you, Annie and Sarah, seriously, for being wonderful mentors and for working with me throughout the years. Also, thank you to all of the other co-authors who have contributed to this work, whose faces you see on this slide. They've been great peers and friends to me as well, and great contributors to the work that you'll be seeing. So thank you to all of them. I'd like to also thank Zach and Amir for also taking the time to be on my committee today. Both of them are people who I've taken multiple of their classes at CMU and learned a ton. So it's a joy to be able to learn from them and to see them be on my committee today as well. So thank you. And finally, thank you to all of my peers in the musculoskeletal biomechanics lab and the microrobotics lab for being just wonderful friends and peers and people that I've gotten to learn a ton from and alongside of them throughout the years as well. So thank you. So without further ado, let's jump into the presentation. So all the work that you'll be seeing today is motivated by the simple fact that motion is not only essential to how we survive as human beings, but also how we express and explore what it means to be human. So when we do things like music or athletics, we're really precisely controlling our body from our muscles to our joints to achieve a very precise and controlled motion of movement. And so this can be really fun and inspiring, but unfortunately, not everyone in the world has the same ability or access to the ability to control and move their body around. Unfortunately, right now, about 20% of individuals in the world are suffering from a mobility impairment that reduces their ability to locomote and impacts their quality of life. And about 50% of all of us are expected to have one of these mobility impairments in our lifetime. And these numbers are actually thought to increase in the future as the average age of our global population continues to increase. And these are not just far off kind of experiences. These are very intimate experiences, right? So things like knee osteoarthritis, which affects about 5% of adults right now, and 20% of adults over the age of 50, is where, let's say you have a healthy knee here, right, where you have this joint spacing, but as you have knee osteoarthritis, your cartilage degrades over time, and it can make it very painful to even walk, move around. And this happened to my grandma, who's actually on the call, so shout out to my grandma, who had to eventually have a total knee replacement. And so, this is a very painful experience for many people, and it takes a long time to go through physical therapy and get back up and moving on your own. And so one exciting thing is that through our study of human motion and human biomechanics, we have gotten to the point where we are able to understand the body and simulate the body with enough accuracy to actually help design some interventions for some of these mobility impairments that are very problematic. So for things like cerebral palsy, for instance, one of the most common negative gait adaptations is a stiff knee gait, where you see an individual has a very reduced range of motion in their knee. And that's very dangerous because that can lead to tripping and falling, right? That can be very painful and destructive. And so one experimental strategy that's thought to try to help this would be to take the rectus femoris muscle, which is thought to help, right, extend the knee, which maybe is being overactivated for a cerebral palsy patient and stopping them from kind of swinging their knee as they're moving, to take this muscle and move it surgically to another muscle location. But now that we can do this with a biomechanical understanding and musculoskeletal simulation, we don't actually have to just go in and do the surgery. We can actually use a model to try to do the surgery in simulation first. So we can take the muscle pathings of this rectus femoris, we can actually try to move it to different muscle pathings and muscle groups and see how that affects the force that's generated by these muscle groupings on the knee and the underlying knee range of motion that comes out of it. So this is really exciting. It kind of shows you how we would like to use these musculoskeletal simulations to try to overcome some of these gait impairments. But unfortunately, there's a lot of impairments that are out there that are still very difficult to treat. And a lot of that has to do with the fact that our ability to study and understand people's motions and their biomechanics is still insufficient, especially when we start to move into the real world outside of constrained laboratory environments like this. So traditionally, we would capture an individual's motion using these stationary infrared cameras, these motion capture markers on their body, and an instrumented treadmill. When we use that technique, we are able to learn, though, about the joint angles and body forces with enough accuracy to try to inspire or design a lot of these rehabilitative treatments. We would like to do the same thing by using totally wearable, portable sensors that can go on an individual into the real world. And we want to do that for a couple of reasons. One, we would like more time points and data points in our analyses to track someone's motion and how it's progressing over time. And two, we know that individuals behave very differently in the real world than they do in these kind of isolated clinical or laboratory spaces. One, because their tasks are very different when they're, walking upstairs or dodging someone to get into a subway or something like that, right? But also because when you just watch someone's gait in the laboratory, we know that they start to behave very differently. So what's exciting is that in this pipeline, where we try to do this musculoskeletal analysis, predictive simulations are starting to become less of kind of a bottleneck to this process. So we can now comfortably do some of the most complex simulations with thousands of decision variables offline within a few hours. And this can be used to do things like, once we have some of those marker-based motion capture dots, which you can see here on this model, once we have some of those, we can even predict what the contact forces between the ground and the feet would have to be to produce that observed motion with some decent accuracy. We can also approximate what the muscles would have to be doing to produce that desired motion. So how are the muscles being activated by the body, and how are they producing force to generate the motion that you're seeing? And so this can be really useful. But a lot of the challenge now is focused on how do we find data that we can then use in this musculoskeletal simulation pipeline to do the similar things that we can do in the lab, but wherever an individual is going in their daily life. So there's a couple ways to try to accomplish that. One of the methods that's been explored throughout the biomechanics field is to use wearable sensors. These are things like inertial measurement units, which package together an accelerometer and a gyroscope and magnetometer to try to assess the orientation of a body segment. Things like instrumented watches or smartwatches that try to track varying different information about the skin and maybe your epidermal activity. And things like instrumented insoles that measure pressure and then try to infer ground reaction forces from that. So at state of the art, how this would be done, or one method to do this, is to take these inertial measurement units on the body and to use a sensor fusion filter or a state estimation filter, like a Kalman filter, to estimate the orientations of these body segments. And then once we have those orientations, we can use a scaled musculoskeletal model and match up the virtual IMUs on this model to the body. And that can give us some estimates of the joint angles. However, this process is still pretty far from matching the accuracy of our traditional motion capture measurements. It gives you some pretty large errors. On the other hand, there's techniques like computer vision, which have received a lot of attention as well. And this is where you'd use the fact that, in our society, there's cameras everywhere, right? Like smartphones. And we can take some of those images and we can have experts label those images with where the key points should be on the body. And we can train neural networks or deep learning models to try to predict those key points onto the images. And then we can triangulate those images to get three-dimensional key points, as I'll refer to them, or estimates of the joint centers of the body. And then we can try to extract joint angles and kinematics from that directly. Unfortunately, this also has a lot of error that makes it a lot less accurate than marker-based motion capture. So there's still some gap here in getting closer to what we would like to be when we're taking some of these traditional methods into the real world. So these last two approaches I talked about with IMUs and computer vision are focused on body kinematics or joint angles, and as well as kinetics or joint forces. But another really important thing that we like to sense to assess health is muscle behavior, or specifically muscle activity. And so traditionally, this is assessed in the lab using electromyography, or EMG as it's shortened to. And this is a technique that measures the voltage difference across your muscle as your body is recruiting that muscle to produce muscle force. And we call that neural excitation. And when we measure that excitatory profiles, we're able to assess whether someone is behaving, their muscles are behaving maybe as they should or in a non-traditional way. So traditionally, this is measured in the laboratory using these discrete sensors. Oftentimes, this was recorded using wired sensors. Nowadays, it's mostly short-range Bluetooth. And there's a lot of ongoing work to try to move this into the real world in a way that's reliable and very consistently accurate and matches kind of those lab-based techniques. But there's a lot of limitations here that are still being addressed. Things like battery life is very challenging. Bandwidth limitations are very challenging. Maintaining consistent conductivity between the electrodes and the skin is very challenging. And so there are people that are still trying to make these into a form factor too, like athletic shorts that can be worn during exercise. So you don't have to have an expert placing them on the exact location where they need to be placed. Unfortunately, a lot of these newer kind of commercial approaches that are trying to implement them in a more portable form factor are not extensively validated against the in-lab techniques. So for this example, the green is the kind of in-lab approach and the gray is a textile that's being developed commercially. And you can see that if we're looking at a squat for an individual, we have their hamstring signals, and the gray here kind of matches the green one. So this seems like we could maybe use this signal as a stand-in for our in-lab kind of gold standard EMG techniques. But at the hamstring groups, we see this very strange artifacting that starts to happen. And so if you were to design an intervention based on this information, you might be actually moving your patient in the wrong direction. And so that would be something that's kind of scary and shows the need for this really extensive and consistent validation of these techniques. So all the work that I'll talk about now is in my thesis has been trying to contribute to bridging the gap in accurate portal sense. And so we can get similar accuracy to in-lab approaches in the real world to try to inspire more widespread musculoskeletal well-being. And so I'm going to talk about 3 projects that I've worked on to do this. The first one is where I designed a novel computational algorithm to estimate biomechanics by fusing IMUs, videos, and biomechanical models. The second is a project where I characterized capacitive sensing as a portable muscle activity tool for the first time. And the third is a project that looks into physics-informed machine learning and how we can apply that to specific ongoing portable biomechanics sensing challenges. So I'm going to start with this first one here. And this one is work that is published in the Journal of Biomechanics. So I've already talked a little bit about computer vision and inertial sensing and kind of how they can be utilized to try to assess gait in the real world. But they actually have some kind of unique weaknesses that also make them quite complementary to one another. So computer vision is very fast. You don't need to wear anything, so it's not obstructive of the motions you're doing, but it's challenged by occlusion. So if you have a camera that doesn't pick up a certain motion here and doesn't see a body segment, it's going to have to try to figure out and guess where that is, and it'll probably be pretty inaccurate. Second, you need to make sure you have calibrated cameras. So sometimes it requires to be in a calibrated environment. And third, the biggest limitation is that this is totally data-driven. So if you don't have information or training data for your neural networks that are representative of the body type and the motion that you're assessing, you're going to get some kind of unknowable generalization error. So this is providing estimates typically of your joint kind of centers, and it struggles particularly when it's estimating kind of joint angles. On the other hand, inertial sensors are very portable as long as you know where they're placed in the body and you kind of know where the initial pose is. However, they suffer from drift because they're providing information about the accelerations and angular velocities of the body segment. So there's higher order state terms. And so you need some additional way to try to kind of ground this with position level information so that you don't accumulate drift as you're trying to estimate where the body is in space. So you can see how inertial measurement units are providing that rate of change of the joint angles, whereas computer vision are trying to provide position level information. So together, these are actually quite complementary. So there was some prior work done in the lab by some other students that looked at how we could take computer vision methods that give us these 3D joint centers, and you can even match that up to a mesh model of the body that's been derived from a bunch of human body scans. So this is a data-driven mesh model. And then we can actually numerically differentiate these body segments to get their angular velocity in space of the body segment and optimize it such that we match that up to some angular velocities that we get experimentally with gyroscopes. So this is really exciting. It does show kind of the complementary nature of the two, and it did show an improvement. But this opened up a question, which was almost all of this process is data-driven. What happens if we implement multi-body dynamics in this process? Does adding physics laws as a constraint to this process make it more accurate? And so that led to the questions of this first study, which was if we add a physics constraint, does that improve our accuracy of kinematics estimation over an unconstrained fusion approach and over the kind of two single modality approaches, IMUs by themselves or computer vision by themselves? And once we assessed that and did the benchmarking of the different techniques, the next question was, if we have varying qualities of IMU and video data, how does that then change how these different techniques kind of perform with respect to each other? Does having worse or better IMU or worse or better key point data change their performance? So to test these hypotheses, I used time-synchronized IMU, video, and marker-based motion capture data to assess each of these techniques. For the computer vision component, I used the cascaded pyramid network, which was state-of-the-art at the time for doing 2D key point feature detection, and then I triangulated them into 3D space using a weighted direct linear triangulation. And then all the simulations were done in the sagittal plane to kind of make things quicker. So for the proposed method that I've been working on, this one takes your video data and now IMU data. And so we now have inertial profiles of the different body segments, and we have estimations from video of where the kind of joint center should be in the body. But this musculoskeletal model now that we have, or biomechanical model rather, has embedded in it analytical expressions of the kinematics and how they map to where these key points should be and these inertial measurement unit profiles should be on the body. So we have an expression from the Y and X pose of this body and the joint angles that maps to the kind of virtual key points and virtual inertial profiles of the body segments. And what we can do then is we can try to track these experimental video measurements and experimental IMU measurements with our musculoskeletal model. So we can embed those in these tracking terms as J key points and J IMUs are tracking costs we're going to minimize, that are the distance between where the video is saying the body should be and where the body thinks it is from these kinematics. But we're going to do this tracking part while respecting the laws of physics. And that part where we respect the laws of physics can be embedded in this equality constraint. So we have this map now from the state of our model and the control variables, so the forces at the different joints, and how that will propel the derivative of the state of this model. And we're going to make sure that these multi-body dynamics or these laws of physics are obeyed during this tracking process. And this is solved using optimal control techniques, specifically direct collocation. And we not only estimate the body kinematics, but also the body dynamics and the contact forces of the feet to generate that desired motion. And so I'm calling this constrained fusion because of this equality constraint. And I tested this constrained fusion approach against an unconstrained fusion approach that doesn't have this equality constraint. And this one doesn't have physics. It only is tracking the key points in the IMUs with the kinematic expressions from the body to those different profiles. And I also tested these two fusion approaches against a single modality approach from IMUs that was state-of-the-art at the time, and a single modality approach for video that is also state-of-the-art at the time. And what I found was that when you do this comparison, the video-only approach does really well at estimating the position of the body, but a lot worse at estimating the joint angles. Whereas the IMUs are decent at estimating the angles, but a lot worse at estimating the position. But when we do this fusion, we're able to do both quite well. And adding the physics in does improve the results, but not by a statistically significant margin. So if we just look at this part, it seems that the fusion techniques are better because they're able to, again, leverage this complementary strength between the two techniques. However, maybe adding that fusion constraint, which also increases your computational cost, might not be super essential all the time. But I wanted to look at how that would change when we have different levels of IMU accuracy or key point estimation accuracy. So for instance, if you have individuals with a lot more soft tissue motion on their body, we might not really know where the IMU is in space. There might be some uncertainty, and that could reduce your signal to noise ratio and make things harder or give you lower accuracy when you track that information. When you have less soft tissue motion, maybe you have better IMU data. For key points, this could look like if you're using different computer vision algorithms, maybe that use a single image at a time or single views from only a single camera, or if you're using computer vision methods that take video data and leverage the temporal information between frames or synthesize multiple camera views. So you could get these different range of accuracies when we're really trying to apply this in the real world. And so when I test the different techniques across the spectrum of noise, the way that I did this was I took the experimental data and I chopped off basically the ground truth of what those inertial and key point profiles should be for motion capture to isolate just the noise background here, phi. And then I scaled that noise background up and down to reach each of these different scenarios, and then reran the simulations on the synthetically kind of modified data. And this is useful because I don't have to actually kind of know or assume what the ground truth noise distribution should be. I'm just taking a real world noise distribution and scaling it up and down. And so when I do the comparison to different techniques, what I find is that when we have poor IME data, but great video data, the constrained fusion actually becomes a lot better than the unconstrained fusion and more beneficial to the tracking. However, in the opposite scenario, when we have bad video data, but really great IMU data, all of a sudden the constraint on the physics is no longer helpful, and the unconstrained fusion technique is actually much better. And if I scale things kind of synchronously, what we get is kind of similar to before, where there's not a statistically significant difference between the two. Now, why is there this trade-off that exists where we should or should not add physics depending on data quality? Well, the reason for this seems to be that if you look at what the physics information is actually providing, it's a constraint on the state to the state derivatives, and of course with the controls also in that. But that's very similar to what the tracking cost in the IMUs is actually mapping for us. The tracking cost in the IMUs is mapping from the kinematics of the model to the state derivatives at the IMU locations on the body segments. So there's this overlap in information that the physics and the IMUs are providing. And so it seems that when the optimizer wants to rely maybe on some really bad IME data, having the physics that are better than the IME data in that case is useful for offsetting some of that and kind of denoising where the IME data is noisy. On the other hand, it seems that when you have really, really, really excellent IME data and you have physics that maybe have more uncertainty in the model than the IME data does, then it seems that actually adding those physics is not helpful to the tracking, right? The optimizer would rather use the physics or the IMU than the physics that you're providing. So what does this all mean? Well, kind of coming back to the kind of overview here, it seems that these fusion methods are consistently outperforming the single modality methods across the entire noise spectrum that was tested because of this complementary nature. But adding the physics constraint to that fusion process seems to be particularly recommended when you have physics that are better than the IME data itself and have less uncertainty. And when would this actually occur in the real world? Well, the lower end of kind of the IMU signal to noise ratios I tested correspond to roughly about 5 centimeters of soft tissue motion on the body. So that actually corresponds to about the higher end of soft tissue motion of low BMI individuals. So if you were moving to kind of middle to high BMI individuals, it's likely that having a physics constraint would be useful for maybe denoising some of that uncertainty that you get in your IME data. And so, of course, the main impact of this is providing a framework for how we're going to test some of these emerging markerless motion capture techniques and how we should be choosing which computational approach to use based on data quality. And there's a lot more work to be done here in the future, since this needs to continually be benchmarked on different pathologies, motions, different body types, more degrees of freedom, et cetera, right? So there's more work to be done here, but hopefully this provides a framework for how to do that testing in the future. So that summarizes and concludes the first project I'll be talking about. And again, that's focused on IMUs, videos, and predominantly kinematics assessment. But this next project I'm going to be talking about is focusing more on muscle activity, and it's going to tie back then to kind of full body kinematics assessment as well. And this work is work that has been under review at Nature. So I've already talked about portable sensing and why it's so important to the future of rehabilitative care using things like computer vision and wearables. But there's a lot of unexplored kind of flexible wearable devices that are being developed in the robotics community and other sensing communities that have not yet been fully validated in the biomechanics field. And so we were really excited to look at one particular sensing modality, particularly because it's already very mature and very widely used and adapted in a lot of different industries, and that is capacitive sensing. So if you've ever used an iPhone or Nintendo Switch or played the latest Zelda game, you probably realize that these touchscreens are really robust, have really great battery life, and can create a very seamless human-to-machine interaction in a lot of different natural environments. So the idea was, can we leverage this to assess something actually valuable in the biomechanics domain? So in this project, I'm going to talk about how capacitive sensing can be used to kind of give us a fundamental understanding of muscle behavior, how we can then use that to try to inspire clinical impact, and how we can then assess how to use that as a complementary device to existing wearable sensors like inertial sensors. But before I do each of those, some background on capacitive sensing. So if you've ever seen in like your high school physics class, the parallel plate setup, basically anytime you have conductive charge building up on two surfaces, you have a capacitive coupling that exists between them. And for a parallel plate setup, it can be modeled with the following equation. And you can imagine now that we could create an analogous system that has an electrode embedded inside some felt. And now we have the muscles on the other side, and these are both going to build up charge. And we can then calculate using a capacitive sensor the capacitance between these in this whole system. And that capacitance will change as the distance between these interfaces change and as the muscles start to move. And what's really nice and unique about the setup is that because capacitance is a proximity sensor, we don't need direct contact between these two interfaces. And that's different than some of the other traditional sensors like electromyography, where maintaining conductivity between the skin and your sensor is really important and actually quite difficult in the real world. So we went ahead and built these sensors as a wearable capacitive sensing device. Here's an example at the shank, though I built this at the shank and the thigh. And then here's a cross-sectional view of the shank. And you can see the electrode kind of embedded inside of this. And now you can imagine that as you're toeing off, you're going to step, and you're going to need a plantar flex your ankle. And that plantar flexion is going to require you to contract your gastrocnemius. That contraction of your calf muscle, your gastrocnemius muscle, results in an expansion in the cross-sectional area, or a bulging, and that bulging reduces the distance between the muscle and this electrode. And if you look back at this parallel plate equation, that should roughly result in an increase in the capacitance. And that's what we start to see, is that now we can begin to map out the capacitive profiles as a result of this muscle behavior. Here is an example of the actual sensor schematic on the cross-sectional view. So we have some conductive copper tape embedded between any substrate we like. We use some comfortable felt. We can then use Velcro to kind of tighten these straps here. And then we have a snap connector from a simple sewing kit to create that electrical lead and connection that's going to lead into our microcontroller to do our processing, and then send it to Bluetooth to a computer to do our storage and further data processing down the line. So now that we have these cool capacitive profiles, are they actually useful for anything? What do they fundamentally tell us? So we wanted to test that hypothesis that we're actually measuring that change in cross-sectional area. And so to do this, we can go into the market-based motion capture lab. Here's the capacitive sensing sleeves on the body. You can see that the profiles across the subjects are quite consistent. And we can take our markers now, and we can then scale a musculoskeletal model to the body, and we can now predict what the lengths of the body should have been to produce that motion. And it turns out that the fiber lengths of the muscles are very highly related on their own to the capacitive sensing signal. And if we take all of those fiber lengths and we calculate the composite cross-sectional area change of all of those muscles of each body segment, it turns out that it's a very, very close match for the capacitive sensing signature. So it seems that we really are measuring something fundamentally interpretable in this muscle physiology. But not only that, we wanted to look at whether this is really consistent on a subject-by-subject basis. So to do this, we looked at each of our participants. We collected participants ranging from 19 to 76 years of age. And we were looking to see if there's any trends in how the capacitive sensing signature to that individual's muscle area, how related that was. And it didn't seem like that relationship got worse across participants of different ages, different body mass indices. And we even took MRI data to see how that would change with muscle volume, muscle development, resting fiber length, and fatty infiltration. And it didn't seem that there were any statistically significant trends. So even across a pretty wide range of body compositions, the capacitive sensing signal is very consistently a measure of that muscle cross-sectional area change. We also want to look at how it would compare to traditional measurements of muscle behavior that we would have done in the lab beforehand. So that's things like excitation and force. So here's your capacitive sensing signature of the shank pulled across participants. Here is the electromyography signal, and here is the simulations of muscle force from market-based motion capture. When you take the aggregate of these signals across the muscles, you see that the signals are pretty close related. But if you look within subject trials, actually, the capacitive sensing signature is as related to the simulation measurement as EMG is. So we're already within the realm of similarity of our traditional muscle behavior measurements. And we seem to be measuring something that's fundamentally interpretable, which is pretty exciting. But the next question is, okay, let's say we have a signal and we know what it means or we can interpret it. How useful is that signal going to be at actually detecting changes in muscle behavior in clinical applications? So to do this, we tested two different clinical applications. The first one is a toe and gait modification. And this toe and gait modification is a learned gait that has been developed to try to reduce knee pain and improve knee function in knee osteoarthritis patients. So the idea here is that if we train individuals to change their gait, both in the lab and outside, can capacitive sensing more sensitively detect changes in muscle behavior because of this gait adaptation than electromyography and simulations of muscle force? So we did this experiment and found that capacitive sensing was more sensitive to these gait adaptations than electromyography, both inside and outside, and it was as sensitive as simulations. So this is exciting because it shows that this sensor perhaps has more sensitivity than maybe some of our traditional sensors we would have used to try to assess this behavior, but we can use capacitive sensing instead. Then another thing that is really important is kind of how adept the sensor is and how well equipped it is to actually go into the real world for long duration monitoring. So what's really exciting too is that capacitive sensing has an order of magnitude less drift than electromyography. So the signal doesn't degrade over time as quickly as the EMG signal does. So it seems to be well equipped for long duration monitoring. And also it seems to be a lot more robust to misplacement. So if you misplace an EMG sensor by even a few centimeters or even a few degrees, because of the crosstalk with different muscle groups, you completely lose the signal and your ability to detect those gait adaptations. But with a similar level of misplacement with capacitive sensing, we were able to still detect that baseline toe and modification. So it's pretty robust to both that drift over time and also misplacement if an individual was placing the sensor on themselves. So this is a modification that's meant to be designed to help someone's gait. But what about tracking a gait modification that is actually making their long-term well-being worse? So for instance, that stiffening gait is a gait that commonly occurs after knee surgery, and it can result in long-term complications from healing. And so the question here is, can we use capacitive sensors to kind of monitor this type of adaptation? And it turns out that if you take the baseline and stiffening capacitance sensing profiles and you subtract them and look for the difference between them, and then you look at that difference across participants, there are some trends that really emerge at both the thigh and the shank for detecting how someone is modifying their gait. So this is really exciting because it shows that there's a lot of potential to use capacitive sensing to actually monitor someone's gait if we had a database of how other individuals were changing their gait as well. And we can then go further with this by testing kind of binary classifiers on this data. So if we train binary classifiers to predict a left out subject on this data, we find that capacitive sensing is as predictive of this gait as electromyography, which is great. And both capacitive sensing and electromyography are more predictive than inertial sensors, both when we're training on the raw inertial sensor data or when we're using the state-of-the-art sensor fusion filters to try to predict the knee flexion angle directly. Why is this important? Well, this shows that muscle activity for certain gaits might be more prescriptive of the gait modification than inertial sensors. And so it means that these muscle activity sensors are likely complementary to IMU sensors. However, that opens up another question, which is if we have these two complementary muscle activity sensors, which one is a better complement to IMUs when we try to use all these together to assess full body kinematics? So that's the final test here, is looking at how we can compare these two setups to assess full body kinematics. So I've talked about before how we can use IMUs. If we have a full body setup of IMUs, we can try to detect the orientations and then use a musculoskeletal model to predict full body joint angles. But now there's another option, which is to use electromyography as well and track both what comes out of the IMUs and track the excitations from electromyography with a musculoskeletal model. So for this, we have to solve this with an optimal control problem because these excitations happen before the muscles actually produce force, and that force then causes the body to locomote. So when we track these excitations, we're tracking a control variable in the kind of optimal control paradigm for how we do this tracking problem. And that can be pretty challenging to solve because there's an unknown time delay between when the muscles are actually firing and when they're producing force. And so on the other hand, now because of capacitive sensing and because capacitive sensing is so related to the fiber lengths of the muscles, we can actually predict the fiber lengths of muscles from capacitive sensing directly and track those as our kind of tracking variable. Now, this in theory seems to be an easier tracking problem and a better one for estimating kinematics because those fiber lengths are directly related to the kinematics and a direct result of them. So these are basically adjacent to the state variable that we care about in our tracking problem. So when we actually do this test of each of these simulation techniques, here on the left will be the average subject result, and on the right will be the mean and standard deviation across participants for some other degrees of freedom. And what we find is that IMUs produce some pretty large errors that might not be sufficient for some of the applications we could care about. But adding electromyography can, for some degrees of freedom, actually increase and improve the accuracy. But when we add capacitive sensing, we see accuracy improvements across the board of all the degrees of freedom. So this is really exciting. It seems that capacitive sensing is a better complement to IMUs than EMG because it's providing that, again, state level information that can help overcome the drift that's associated commonly with these IMU methods. So this is exciting, but this is done at full kind of scale on the body, right? So we have sensors on each body segment. It's a lot of sensors to wear. So I wanted to ask the question, what if we try to just track one joint angle with a sparse sensor, a single capacitive sensor above the ankle and the shank? The one potential application for this could be something like ankle osteoarthritis, which is generally looked at or assessed based on the range of motion of the ankle. So if we wanted to do something like this, we can predict an individual's normalized fiber length, and this is normalized with a standard scalar normalization, with just a database of other subjects' data. And once we have this estimation, now this is not really useful to predicting the ankle angle on its own because this is normalized and we care about the unnormalized ankle angle. But fortunately, if we have a scaled musculoskeletal model of an individual's body, we don't even have to use optimal control in the very computationally expensive kind of full physics model. We can just use the fact that in their scaled musculoskeletal model is embedded the information about how long their muscles are. So we can track with a model the fiber lengths that are normalized and predicted through our neural network, in this case, across participants, and then we can let an optimizer select the scale and centering factor to unnormalize this signal while it's tracking it with a musculoskeletal model. So we can do this kind of unnormalizing inverse kinematics approach. And it turns out that this provides very accurate estimates of the ankle kinematic without needing anything but some capacitive sensing data and their scale musculoskeletal model. And this is more accurate than IMUs or computer vision at state of the art. So this is quite promising. It shows that perhaps we can not only use capacity sensors in a complementary way with other sensors, but there also could be some room to use them on their own if we really want to use them in a sparse format. So a lot of exciting things come out of this. One, maybe there's more things we could do in muscle bulging studies or taking this into the wild to understand mechanical behavior, where before we had to use animal models to try to understand how the different aspects of muscle bulging worked in the real world. This could hopefully be used to inspire more clinical applications in the real world with these kind of sensorized garments that could go in maybe some clothing to go on the skin. And third, we're excited about how this could be maybe implemented with device control like exoskeletons and prosthetics, and trying to inform how they should be firing and how they should be working with the individual. Now, of course, this opens up a lot of work for future work, a lot of room for future work, especially because of limitations of the studies so far. So one thing is that a lot of these studies were done with mostly healthy individuals, except for one total knee replacement patient. And they did a lot of mock gaits or training of their gaits as if they were a knee osteoarthritis patient. But of course, there's a lot of need to start to move this into actual clinical populations that have particular pathologies to see if this can really promote different changes in their gait. And with that comes the fact that a lot of this was done using kind of generic muscle wrapping of the models that were kind of used to assess and infer the fiber lengths. But this was, with scaled musculoskeletal models. But if you have an individual who's impaired and has non-traditional muscle physiology, you might have to start to adapt that to match someone if they have an impairment. And third, almost all this data was recorded using a self-capacitance electronics architecture. So there's actually a lot of different electronics architectures behind capacitive sensing. And they should be, in theory, similar, but there's more testing to be done to see how maybe different electronics architectures would change maybe the resolution or the sensitivity of the measurements on gait data specifically. So there's more room here as well from a kind of mechatronics perspective on how to design these sensors. So together, this kind of finishes the muscle activity with capacity sensing project that I talked about. And if you've noticed in both of the past two projects I talked about, each of them tried to use physics to kind of overcome a lack of information when the sensors did not provide everything that we needed. And so in the biomechanics space, there's a ton of different techniques that are labeled as physics informed. And so I'm going to give you kind of two examples to show you the diversity of that. So one example uses inertial measurement units, so these wearable sensors, uses a neural network to predict kinematics, and then uses a full-scale multi-body dynamics of a biomechanical model to track that data and try to smooth it out. This is cool because it uses full-body dynamics, but the kind of limitation here is that these dynamics don't back-propagate and update the weights of the model. It's only one-directional. Another example that's kind of the other side of the spectrum uses computer vision, and it uses kind of a mesh model here, and it will calculate the center of volume of all the voxels of this mesh and call that center of mass. And it will also calculate all the center of volume of the voxels that penetrate some preset ground plane, and it will call that center of pressure. And there's loss functions actually embedded in the neural network that try to help the neural network predict outcomes that match up the center of mass to the center of pressure. So the loss functions back propagate. The limitation here is that this only works on statically stable poses. It was designed for predominantly to be used on yoga poses. And so it doesn't actually have multi-body dynamics that model time varying behaviors. So these are both cool, but neither actually leverage the fullness of the recent kind of developments in physics-informed machine learning or physics-informed neural networks as they're actually defined in that literature. So a physics-informed neural network needs to have a actual equation of motion, so not just a statically stable pose, but equations of motion that back propagate. So the first one didn't have back propagation. The second one was only applicable to statically stable poses. So, and this gives you what's called a physics-informed neural network. So what is an example of a physics-informed neural network? So a common example that's used is where you have some coffee that's hot in the morning, right? And you want to know when it's going to be cool so you can drink it. And so let's say you had a temperature probe in this coffee, you would have some data points here in blue, and you want to be able to predict where this is really going to be in black. So if you were just to train a neural network on this blue data points, you would get some pretty wild errors when you try to extrapolate because neural networks are not good at predicting what they haven't seen. But when you have a physics-informed neural network, you can take this Newton cooling physics that governs this kind of function of this behavior, move the derivative of temperature to the other side, calculate the residual of this, and plug that in as a loss function that updates the states of the neural network. And when you do that, you get really great predictions. You're able to match not only the data that is being provided, but you're also matching the function that is explained by the physics information. So this is really useful for creating faster simulations for then finite element methods in a variety of domains. It can be really helpful for regularizing overfit neural networks. It can be helpful for extrapolating from sparse data, as I've showed you here. And it can even be used to learn physics parameters from data. If you make some of these physics parameters like R and the ambient temperature here, learnable parameters with an initial guess, you can actually optimize to find those from the data. However, pins is not always useful. So if you have enough data points that covers the whole domain, a data-driven approach will produce the same results, sometimes even better. They can actually increase training time over vanilla neural networks, so you have to be careful in when they're actually going to be efficient. And they don't work the same across all physics systems, mainly because their convergence behavior can be very different. So there's a lot of literature out there where you have to chop up certain domains of certain physics problems, otherwise you'll get convergence to strange local minima. So because this hasn't been really widely adapted to the biomechanics space, and specifically not into biomechanics portable sensing, I wanted to look at how we could use pins for 4 applications that are of ongoing interest. One is, can we use pins to extrapolate the rest of the kinematics trajectory if we said had sparse data that didn't fully define someone's kinematics? 2, could we actually use them to denoise, let's say, noisy IMU data? So we have noisy data, can we use the physics to denoise that? Third, can we identify parameters from prescribed kinematics, similar to what the OpenSim model would use as a residual reduction algorithm? So system identification to learn a better physics model when our physics model has uncertainty. And fourth, and probably the most challenging, can we overcome a cross-participant bias? So if we have some data from like 10 participants and we want to learn on the last one, if you were just to train a vanilla neural network, it would again extrapolate poorly because it hasn't seen that individual's kinematics and how they behave. But can we embed the physics from the new participant and overcome or regularize that error? So the simplest way to think and conceptualize about pins in the biomechanics space is probably the following, where let's say you had some wearable sensing data like IMUs, and now we have a neural network, and that neural network is going to help us predict the kinematics of the body and the forces from motion capture, right? We can train that neural network and use it to predict. But now we can take those predicted values, we can plug them into our multi-body dynamics equation of motion from something like OpenSim, and then we can take the residuals of that as a loss function and plug that back into our neural network in a back propagation to update those neural network states. And the hope here is that when we use predict, we have neural network states that are adhering to the multi-body dynamics of that participant. So this is an easy way to conceptualize this, but it's not actually a technique that leverages how pins are developed in the pins literature, because you don't use this generally to regularize. You would rather use it as an ODE solver itself. So this next thing I'm going to show is kind of my approach on how we should be applying pins in the biomechanics domain and leveraging that literature. So let's say we have some initial predictive model, and this is the kind of vanilla neural network technique. So you have some IMU training data, you have some kinematics, you're learning the function from those kinematics to, those IMU data to your kinematics, and you can extrapolate that on some new data and make some predictions. These predictions might have any of those 4 kind of downsides I've talked about. They might be noisy, they might be sparse, they might have a cross-participant bias. Maybe you want to learn some physics from them. So we can then apply the pin as an ODE solver, and that solver is going to use a neural network to match any of those predicted values we'd like to match. So we have some data we'd like to fit to, but we also then can take the neural network and forward roll out that neural network or make a forward pass at any desired time points we have. We take a forward pass at any of our desired time points, and then at those desired not points, we are going to make sure we're satisfying the laws of physics for our system, and also make sure that we're adhering to a collocation loss that enforces the fact that the first derivative has to match the second derivative, and the second derivative has to match the third derivative. And that's, and our hope here is that wherever we've picked these desired time points, we know that we are satisfying the physics laws of that system. And the thing that's somewhat novel on my part in this case is that in a lot of the pins literature, it doesn't have this collocation loss. I found that if I didn't have this collocation loss, things would really break and converge to really weird local minima. It wasn't until I had this collocation loss where things started to work, and that was inspired by optimal control. So when we use optimal control on these biomechanical systems, we have to have this collocation kind of allow it to break the collocation loss early, and that's to basically give it better convergence behavior. And I found it to be the same when we did this in the pins format. So I tested this kind of pins approach on some synthetic data that I could make to have perfect ground truth. So instead of using motion capture data that has some uncertainty and a physics model of someone's body, which would also have a lot of uncertainty, I use kind of synthetic models where I perfectly know what their kinematics are and I perfectly know what the physics are to create that kinematics. And I use a 2-degree freedom rigid body model of the leg, if you want to call it that, and a harmonic oscillator, also maybe a 1-degree freedom model of the leg. And what's important here is that these are useful because they can capture some of the core behavior we want to model of a real system. So if you look at this kind of real gait data, for people of different leg lengths, they have different configuration spaces between the different joints. So this is the hip flexion and knee flexion of myself and my wife, and you can see they're pretty different, right? But if we have a rigid body model, in this case, we can capture some of those changes in configuration spaces in both cases, and at least create some kind of toy models that we can play around with to see how our pins is performing before scaling it up. And so now I'm going to present kind of the results of those 4 test scenarios I talked about. So on the left here, in each case, it's going to be the 1-degree freedom system, which has those multi-body dynamics. On the right, it's going to be the 2-degree freedom system, which has those equations of motion embedded. And in blue here, you can see on the left, I've given this kind of neural network some training data, right? But it's really sparse. If you learn with a vanilla neural network here in gray and try to predict the rest of the domain from that, you get some really crazy extrapolation, similar in this case. But if we embed the multi-body dynamics, even just giving it a few data points and the dynamics is enough to actually accurately predict the rest of the kinematics trajectory. So this is really working, even for systems with coupled equations of motion. So it does enable extrapolation from sparse data. The second test scenario is noisy data. So I took some data here and I gave it some Gaussian noise and some bias. You can see it's offset, it's really noisy. And actually, similarly, if you embed the multi-body dynamics, it actually, all the different test scenarios with either Gaussian or bias noise is nudging the solution back towards the ground truth here in black by over a factor of 2. So it does seem to be useful for denoising. Third is, can we estimate the biomechanical parameters by making some of the system parameters learnable parameters in our neural network? So in this case, I was trying to learn L. So I gave it an initial guess of 0.5 meters, so half of what it should be. And I only gave it some data points. And then the physics-informed neural networks was able to not only predict accurately the rest of the trajectory, but it also was able to predict fairly accurately what the length of the harmonic oscillator should be. And there's a similar story for the 2-degree freedom system when I was trying to learn the length of the shank, or segment B, if you will. And so even with some sparse data, it was able to match the trajectory pretty well and predict the leg length with some fair accuracy. And there's a trade-off here where if I were to give data from the whole trajectory, I would get virtually perfect estimation of those parameters. So yes, it seems that PINS is able to accurately estimate these biomechanical model parameters. And fourth, again, the kind of final boss, if you will, of this challenge. So I'm providing some training data in blue from one person's kinematics in gray here. But I'm going to provide physics now from the second individual's body, and that's in black. And I want to see if the pin can move from just predicting the gray to predicting the black, right? Because that means that would be overcoming kind of the bias that would happen if we were just extrapolating from the first participant's data. When we do that, we see that for the 1-degree freedom system, we get a huge increase where it's starting to match the second person's physics, even though we're providing data from only the first person's. We see a similar story with a 2-degree freedom system, but there's some other artifact in here because it's trying to do two things it's not really supposed to do, right? It's trying to match this data and match the physics, which have some contradictions. But what this shows is that there is potential for yield, for better kinematics accuracy, if even though we only have data from other subjects, we can embed the physics from a new subject. So there is improvement to be had from PINS in this way. So to kind of recap, it seems that PINS are fundamentally applicable to extrapolation, physics-based denoising, parameter ID, and across participant regularization. But there's a lot of limitations in that, and the main one being that I only tested this on a 1-degree freedom system and a 2-degree freedom system. The 1-degree freedom system took 10 minutes to train each of these times, so 1 minute to 10 minutes to solve when I applied the pin. The 2-degree freedom system took 9.5 to 10 hours to train. And so that's a pretty long time, and that's a pretty huge scale. And if we were to assume that this even scaled linearly, which might be kind of a more conservative estimate, then we would be up, once we get to those kind of full body models we like in biomechanics, we're at really, really expensive simulations. I think there's a lot of games to be played here to try to make this more computationally efficient. We can query the dynamics less. We can query them not every iteration during training. We don't have to query the dynamics at every knot point necessarily. We can choose some random knot points. So there's a lot of ways to actually save on computational cost here. But I think that's where a lot of the future of this is going to be, is can we scale this up and can we make it feasible for long duration, or for, full scale applications with PINS. So that concludes this third project. To recap, all of my research has contributed to trying to make portable sensing much more accurate and ideally match the accuracy of some of our in-lab approaches by showing that first, it seems that yes, fusing IMUs and videos can be used to overcome their individual limitations, and incorporating physics can be used to denoise some of those results when the physics are better than the data that we have. Second, capacity sensing does seem to be very useful as a real-world muscle activity sensor, and is a powerful complement to some of the existing wearables like inertial sensors that have been used. And third, physics-informed neural networks do in fact seem to have the potential to help overcome some of these really distinct portable biomechanics sensing challenges and are deserving of future work to try to scale them up and apply them at scale. And so kind of summarizing all this work, as I've worked on this and reflected on all the things I've found, I think that the future of biomechanics and portable sensing will increasingly emphasize the following. The first, to continually synthesize more of these different sensing paradigms to offset their weaknesses. I think that's going to be continuing to be a trend. Third, I think that we're going to continually need to try to intelligently incorporate physics information where maybe our sensors have some uncertainty we can't overcome. However, I don't think that there's going to be a one-size-fits-all approach that has one set of sensors that are optimal and one computational approach that's optimal for detecting every type of thing we care about the body for all the pathologies, or even all the kinematics for all the different types of movements we can do. Instead, I envision kind of, as the community continues to work on this, a list of best practices where we locally optimize the best sensors and the best, most efficient approach for each application. So maybe you don't need to use physics for just the ankle angle, but maybe you do need to use physics if you care for full body dynamics or kinematics, right? So I think hopefully we can kind of locally optimize and tone in on each pathology or clinical application and find out what is the best sensing system and computational approach so we can promote more widespread musculoskeletal well-being. And that concludes my presentation. Thank you so much for your attention, for your time, and I'm really looking forward to hearing your questions.